invariably most machine elements would have a shaft, and uh, when you have a shaft, the reason you want to have a shaft is because the shaft acts as a place where you will fit in elements such as gears, pulleys, bearings, so that you can transmit forces across, right? So shaft is like the most important, it's like the heart of a machine element. So this section sort of covers some of the things you need to keep in mind when you think of the shaft layout. Okay? So what does shaft have? It has usually things like shaft holds gears, pulleys, bearings, etc. So when you talk of the layout, there are some general recommendations, and I just cover a few of them. You want to read the book if you want one of these things. So how do you support shafts? You have bearings. Okay. So what you do is when you are trying to introduce a shaft, you want to put it between two bearings, and those bearings will act like simple support. So the cross here denotes the bearing, and let's say that we want to put a gear. So let's say that's the gear. So the shaft connecting the two bearings. This is not a bit. This should be this. That just shows the teeth of the gear. And so what we have here is bearings, and then this is a gear. And so here we say that this is a good design because the bearings are on the edges, and when they're on the edges, they act like simply supported beam. And then you can essentially analyze this like a beam, right? You have reaction forces and find the reaction forces, and then find the shear force, bending moment diagram, and go on from there. What might consider a bad design? A bad design would be when you're trying to load these like a cantilever. So let's say that we want the same setup, we want a gear, but we change the setup to be something like this. Okay, so it's the same elements, but they are arranged such that the gear is on the edge. It's not simply supported. So this is a bad design, something which you should avoid. Cantilever. So cantilevers lead to higher deflections, and something which you want to avoid is having higher deflections when things move. So avoid cantilever as much as possible. Now, there are cases where you have to, or it's advisable to have a cantilever type of support, and that is when you have a transmission element like a pulley or a sprocket. So avoid cantilevers. Okay, however, here is a contradiction. So transmission elements, two if I can think of right now, were pulleys, such as pulleys and sprockets. So what is sprocket? The the chain on a bicycle is on a sprocket. So you know what a sprocket is. It's basically that circular thing which is basically where the pedal and the chain are connected. Okay, so that's a sprocket, and those act like transmission elements, and those things you want to put them as a cantilever. So here is the setup. This is, in this case, a pulley, but you could put a sprocket too. Pulley. Okay, so why do we put a pulley or a sprocket on a cantilever? It turns out that you'll mount these things on belts or chains, and when you want to do that, it's much more convenient to have cantilever so that they don't really hinder with the bearings. Right? If you put it in the middle, then it's just like a hassle to put the chains and pulleys, sorry, the cables or transmission elements on them. So on these are placed at the edge so that they can be used to mount pulleys, chains, and belts. Okay, some other things. Avoid long shafts. Clearly, as the shaft size grows, you'll see that, and they're simply supported, you'll see that deflections also increase. Low for the same load, you'll have a bigger moment, and so you want to avoid those things. So avoid long shafts, or rather, let me just put it this way: keep shafts small, keep shafts short, ideally on two bearings. Okay, why short? Short implies or short shafts low deflections, low moments, and low moments with low stresses. Okay, now the other thing you want to do is when you have these shafts and you have the bearings on the edge, you have an option of putting the gear somewhere on the shaft, right? You want to put it in the middle, you want to put the edges. The more closer you put to the edges, that is near the bearing, the lower the moment produced by those elements. And so that's it's a good idea to put them at the edges. So put the load carrying element near the bearings. To reduce moments. Okay. So now sometimes you cannot have short shafts. If you have long shafts, so in that case, you're stuck with long shafts. So if long shafts are needed, one might need greater than two bearings, which is fine, but then be mindful about alignment of bearings. So if the bearings are not aligned, then they would lead to unnecessary forces in the radial direction, and that will introduce stresses, unnecessary stresses, and that's not good. So it needs a higher tolerance if you're trying to have uh, more than two bearings. The final thing, and there are a lot of things in the book, but let me just say a final thing. Shoulders and shafts is a great idea. Okay, so what is a shoulder? It's basically when you have shaft of a different diameter. So that is a shoulder. Uh, the reason why you would not want to have a shoulder is because the moment you have a shoulder, you have stress concentration, and the bigger the diameter, more the material, it makes the shaft heavier. But then what happens is if you have shoulders, you can smartly use the shoulders to transmit axial loads. Okay, so shoulders and shafts enables transmission of axial loads. Okay, what I mean by that is, imagine there's a shaft and we have a shoulder on the shaft. So there is another element which shade that. So let's say this is a shaft, this is in housing, and this is subject to some axial loads. Now you see that the advantage of the shaft is that because the shoulder, it can carry that axial load. Shoulder helps support axial loads. So in general, there are many such recommendations, and I would recommend that you, if you, the way this is done is you want to really uh, think of what you want. Let's say you're designing something and you're in need of A, B, C, D components. Then you want to give a thought. You just go read the book, see what the recommendations are, and then use that. And then each thing you do in this case has pros and cons. Like for example, simply supported is good, but if you want to transmit elements, to have something like belts or chains, you simply supported is a bad idea because then it's harder to mount the chains and belts. So the recommendation is read section 703 in detail. And I would do that if you are thinking of a project involving shafts, right? So if your senior design is, for example, on the need to have a shaft carrying loads, then I would just go through that. In fact, that's what I would do, which is now that you've gone through this course, if you want a spring, and we're not going to cover spring because there's too much material to cover in a single class or a single semester, you would just go to that chapter and see what the recommendations are, and then based on that, pick the right way to go about choosing a spring. Yeah. I work at a facility, and the number one failure that we monitor is bearing clearance failure. I see. For all the reasons you just listed. I see. I see. Yeah. Well, yeah. Like industrial machines, so bearing clearance, like the biggest failure. Right. And there is a whole. There are 2 or 3 chapters in the book about bearings, and so designing bearings is another thing. So in fact, you really don't design bearings; you just choose the right bearings and you go with it. But sometimes it's good to know the theory behind it. Yeah, I wish the course was structured where you're actually making choices and loading and getting things to fail in simulation or hardware, and then you understand what those things are, because you may write so many things, but it's only when you have some practical exposure to these things you really understand how they go. So anyway, we are stuck with what we have. Now what I'm going to do then, this is the last section, is we're going to take the tools we learned in the previous chapter on those failure criterion for static and dynamic loading, we had these Goodman line, Langer line, Söderberg, and so on, and then see how to use those to design a shaft. Okay, so shaft designed for stresses. Okay, usually the question is, you have a choice of shaft diameters, and you sort of have figured out what is the layout of your shaft, what are the bearings and gears, pulleys have already been placed, or you've thought about them. Now you need to figure out what is the right diameter of the shaft, and how do you do that? So this is assuming that you know something about the loading conditions in the shaft, that you can go about using some of the design criteria. So the first thing you want to do is find critical locations. This is something which we've been doing throughout the course. We said that a certain point we think has a hunch that there's a maximum load or so maximum stress. We take that point and we design based on that stress, because if we don't find those critical points, then there's no point in choosing points where the stresses are not going to reach the maximum. So we need to find those critical locations. If you have a software, then like finite element analysis, some of you might have used, it'll actually give you the stress distribution throughout the shaft. That's a great way of figuring out the exact location where there will be a critical load. If you don't have that, then you need to basically make some guesses as to which part will be critically loaded. Things like the smallest diameter shaft would be this, wherever the diameter is small, the stresses would be high because stress is inversely proportional to the diameter. That's one hint. The other thing you could think about is stress concentration. Wherever there's a change in geometry, those places would have high shaft. So figuring out those critical locations of high stress is a matter of partly a matter of experience, but partly a matter of just making guesses and then making those calculations. What's that? So this is, we're talking about a shaft has some loads, right? And then you want to figure out, first of all, where along the length is the stress maximum, and within for a particular section, is it at the outer surface or in the middle surface? So it's just a matter of what we've been doing before, which is bending moment shear force diagram, and use that. I don't see how integration can be used. Okay, so what are the critical locations? So here are some suggestions on what might be the critical locations. So outer surface. Okay, so outer surface is if you have a shaft and it's subject to bending, or if it's subjected to a torque. So bending is about this axis, torque is about, let's draw this again. When you have a shaft and okay, so when you bend it, you're going to load it this way such that the axis of bending is this. When you torque it, on the other hand, the axis for torque is this way. Right? They're about different axes. That's what I'm trying to do. So the reason I drew torque and M is because the maximum stress, sigma, is max. Sorry. So on the outer surface, that is on this edge, you'll see that sigma is max and sigma depends on M. Right? In fact, the formula is sigma is my divided by I. The shear stress due to torque is max. This is the outer surface, and that is because of tau. So the shear stress depends on torque, and then we saw the formula for that is T times rho divided by J, right? Now, this is a mistake which many people did in their, or almost everybody did in their second exam was they did not really understand where exactly the maximum shear force acts. It's always on the outer surface. If you, the other points which are critical, which are the inner surface, and that is due to a shear force. So if you have a force which is we call that V, and that force V is acting on this face. So then in that case, the tau due to shear is max. Here, tau shear depends on V. Okay, so the formula for T shear is V divided by the cross section area, right? And so that stress is maximum at the inner surface along the diameter, sorry, along the center. Okay, so the mistake people did in the homework in the second exam was when they solved for the maximum shear stress, right, which comes from Mohr circle, they took this stress as sigma and this stress for tau, and then use the equation for the maximum shear stress. But the difference is that this stress is maximum at the outer surface, and this stress is maximum at the inner surface. So you just can't add something which is maximum on different. In fact, the shear stress is 0 on the edges, and it's maximum at the middle, and the stress due to M is maximum at the outer surfaces, and it's 0 at the inner surface. So it's just as meaningful to add. So be mindful about that when you are solving problems. So here's that distinction. Then there are other things like axial loads. Okay, now the axial loads are such that they give uniform stress throughout the cross section. So if there's an axial, okay, let's say there's an axial load P, then axial loads lead to uniform normal stress, which is sigma equals P divided by 8. So that stress is, that really doesn't give any critical locations. It's actually distributed throughout, but you should not forget to add the effect of P. The other things which you need to be mindful about is stress concentration. The stress might be not that high at a particular point, but because there's a change in geometry and there's a stress concentration factor of 2, now suddenly you see that stress which is 1 unit will become 2 units because of that stress concentration factor. So always find the stresses at the places where there's change in geometry. So the recommendation here is draw shear force diagram, force bending moment, and torque diagram. Once you draw these diagrams, you'll find where the forces are maximum. And once you know the forces, you can find where the stresses are maximum, which again are distributed over the cross section, right? Which I just talked about in a bit a while back. And then once you have that, then you can use those to design. Okay. So with that general recommendation about where the critical locations are, let's come to the actual stresses. And this is basically a overview of what we have done so far. There's nothing new here. So shaft stresses.
When you say draw shear force and pressure in the diagram, you really only need one, right?
You need both. because shear force diagram, so the shear force diagrams tells you about the shear forces or shear stresses. The bending moment diagram will give you bending the normal stresses, and those are different. No, because the place where the bending moment is maximum doesn't correspond to the place where the shear force is maximum. Right? There's this formula is TV.
I thought where the bending moment diagram goes to zero, that's where the shear force is.
Yeah, but that's not always true. I mean, let me correct myself. So that's true to an extent, but there are you can see there are some problems in the homeworks where there were at least 2 points where the shear force and bending moment, the shear force and bending moments were important to be considered. The reason why you need to do that is because there's a scaling effect, which is one of them is my divided by I is the stress, and the shear force is P divided, sorry, it's V divided by A approximately. And so what you need to do is, depending on the value of M and V, you might see that they would have this effect that even though the shear force is not very significant at that point, it actually gives rise to this. I think there was a problem in the book, I think, sorry, in the one of my homeworks where there were 2 points where you had to look at the stresses, and I think it was not very intuitive which one of them. I just am blanking out on that question. I think it was an I-beam or something like that. So I would be skeptical. I would just try to do it for multiple points. Okay, so shaft stresses. Now we are looking at a general case where there is alternating stress sigma A, and then there is a mean stress sigma M. So the stress is Kf M A C divided by I. Okay, so sigma, you know what, let me just write this. Let me write the formulas down and then tell you what these notations are for. So Kf is the stress concentration, Ma is the moment due to alternating load. What I'm going to do is try to simplify this first, so the moment doesn't change. C is in this case, we're looking at a shaft which is of circular diameter. So this is D. So C, which is the distance from the neutral axis, is D divided by 2. And then the moment of inertia is pi times D raised to 4 divided by 64. So if you simplify this, you get 32 Kf Ma divided by pi dq. Okay, similarly, you can write sigma m, which I'll write down a little bit later, but sigma m is the average stress, the mean stress is 32 Kf. Now that's due to the mean moment mm pi dq. So that is all the normal stresses. So then we have shear stresses due to torque, and that is Kfs, which is the stress concentration in shear, times Ta times rho divided by J. So Kfs, Ta is the alternating torque. Rho is the radius. So in this case, the stress is maximum at the outer surface. So I need to put D divided by 2. And then the polar moment of inertia is pi D raised to 4 divided by 32. So simplifying this gives 16 Kf Ta divided by pi dq. Okay, I can write the same formula for Tm, which is the mean torque. So tau m equals 16 K Fs Tm pi d cube. Okay, so now let me write down all those, the notation. So okay, Kf KFS are stress concentrations for normal and shear stress. They come from the tables which, or sorry, the figures which I'll be giving you, or they're in the appendix. So MA, MM are the alternating and mean bending moments. TA, TM are the alternating and mean torques. And then the D is the diameter. So there's a lot of formulas now. So we have ductile materials, they're brittle materials for, so we'll ignore brittle materials for a while because we are only normally design things with ductile materials. So within ductile materials, we have to use a failure criterion. So you have maximum shear stress and distortion energy. We've seen that the maximum shear stress theory is conservative. So distortion energy is much more better than maximum shear stress. So we'll stick to maximum shear, sorry, distortion energy theory for the rest of this chapter, okay? So for distortion energy theory, we need to use the von Mises stress. So we'll define the von Mises stress and then use that within the failure criterion. So let's say the von Mises stress. So the formula for von Mises stress is sigma prime equals square root of sigma square plus tau square, 3 tau square, right? This is for uniaxial. So maybe I just put sigma x tau x y square. And this is when the element has some normal stress, sigma x, and there's shear stress, but no sigma y. And that's the case we're looking here. We're not looking at a case where there's sigma y because in beams, we don't see that sigma y. So that's the formula. So we're going to use this formula to find the von Mises stress for alternating load. And all we do is now replace sigma with sigma A and tau with tau A. Okay, but sigma A, you can go back to the formulas I wrote on the previous page. We can write it in terms of the moment MA. So comes out to be 32 kf MA divided by pi d cube squared. So I just substituted blindly from the previous page. And then we have the shear stress, which is 16 kfs TA divided by pi d cube square. Okay, so this whole thing has to be under the square root sign. So we can write a formula for the mean stress. It's just a matter of replacing sigma with sigma m and tau with tau m, and then go back to the previous page where I wrote down formulas for sigma m and tau m. So that is 32 kf mm divided by pi d cube plus 3 times 16 kfs TA divided by pi d cube square. So this can be simplified a little bit further. Sigma A prime. So this is the first equation. Is 16 divided by pi d cube 4 kfma square plus 3 kfs TA square. And this whole thing should be under the square root sign. And then sigma m prime can be simplified as sigma m prime equals 16 divided by pi d cube. Yeah.
16 by 2 square root of
No, that comes outside. It's not in the square root. Okay. So another now just occurred to me. Uh, so this coming back to your point about shear force bending moment diagram. So although the maximum shear force occurs where the m is well there's well there is a, let's write this down, b equals dm by dx, right? So dm by dx is 0, means that v achieves a maximum. So dm by dx equals 0, v is max or min. So that's the criteria for achieving a local minimum, right? So what we expect is this implies that, so second derivative gives us a test for maximum minimum. The reason why I need to still check v and m, that was the original question, is because they achieve the maximum stress is at different locations. So one of them has a maximum at the center and the other has maximum at the top. And then when you put into the fact that sometimes you're asked to compute not the stress due to M or stress due to V, but you're asked to find the maximum shear stress, in which case you need to look at the principal stresses, which means that you need to find the combined effect of M, V, and maybe some other loads. Then it becomes a lot more complicated than just looking at one of the diagrams, and you need to really look at most of all of them. So it's the combination of the loads, one. Second is the fact that these loads appear at different places are the reasons why you need to go beyond just drawing one diagram. You need to draw both of them. Yeah, and then, if there's torque, you want to go torque, because then the torque will give you a shear stress, which will also show up here. Next. That, yeah, helpful?
yeah.
Okay, so now what we'll do is, now we have these formulas, we'll get into failure. Okay, so far we have the criteria for failure, which is distortion energy. We still need to use the failure theories, failure criterions to figure out if this material is safe, or if you have a factor of safety, then what is a good factor of safety? So we will, now this is actually taking what we learned in chapter 5, that is the distortion energy theory, and combining it with the failure criterion, which we did in chapter 6, into a combined theory. So we call this the DE, which stands for distortion energy, Goodman criteria. So DE means distortion energy. So this A. Okay, so what's the equation for distortion energy theory? It's basically 1 divided by n equals sigma A prime divided by SE plus sigma m prime SUT. So that's the design criterion, right? So if you're given a factor of safety, or if you want to find a factor of safety, you'll sub in the value for alternating stress, mean stress, and these are material parameters, SC, SCUT, and you'll find a factor of safety in. So you could do this in principle and use these equations for sigma A and sigma M, right? I've already written down the equations. But what we'll do here is we sort of combine them into one, and that way you have one equation which you need to use to figure out what the factor of safety is, if that's what is asked. Or it could be another question, which is you'll be given the factor of safety and told to figure out what the diameter of the shaft is going to be. So that's another formula. So what we'll do is we'll combine them. So I'll just call this something. Let's call this, say, the Roman I. And so substitute I in 1. And when we do that, the expression will look very complicated, but it's one place which you can use to figure out what the factor of safety is instead of remembering or using two formulas. So the left side remains same, and then I sub in the value of sigma A prime and sigma M prime from I. So we have 16 divided by pi t cube, that comes outside, and then we have 1 divided by SE 4 times kf ma square plus 3 times kfs ta square, and I need to take the square root of the whole thing. That's only the things in the bracket or the curly bracket. And then I need to do the same thing for the second part for sigma m prime. So that is 4 kf mm square plus 3 kfs tm square, and then I need to do the square root of only the thing in the curly bracket. Then I close the bracket. If it's easier, this part should be on the square root sign. So this is solving for n given d. Okay. We can also write an equation for d, which is the diameter. And so that expression is, well, it's as, I can do some, it's easier for me to copy paste this. So it's the same thing, but I just need to move the d around. Copy. Okay, so what I need to do here is I need to move this d and n around so I can solve for d instead of n. So this d goes, this n goes here, this d goes there. And since it was d cube, I need to take the cube root of the whole thing. Let's put this big bracket, be 1/3. And then we'll see a problem where we get everything together. TE. Gerber. Okay, so what's the equation for the Gerber criteria? Well, it is 1 divided by n equals sigma A prime divided by SC plus sigma M prime divided by SUT square. My bad. This should be n times sigma A. Let me just write it again. So n times sigma A. I was missing the n. SC plus n sigma M divided by SUT, the whole squared, equals 1. That's it. So then what we can now do is solve for n. The reason why this is slightly more challenging is because you get a quadratic equation in n, and so you need to use the formula for solving quadratic equation, discriminant and so on, and then you get two roots. One of the root happens to be negative, which you discard. The other root is positive, and that's the one you're after. So that root comes out to be n equals half SUT divided by sigma m prime square.
That like prime at the bottom there?
Yeah, 2 sigma m. This should be prime too.
Sigma m prime.
Sigma a prime SC. And I'm using prime just to denote it's a von Mises stress. Plus square root 1 plus 2 sigma m SC divided by sigma a, and this should be a prime sigma a SUT, the whole square. Okay. Okay, let me see the notation I used. We'll call that 1. Let me call this. I call that capital. Okay, I called it the Roman 1. See. Okay, so let's call this 2. Okay, so what I need to do is I need to substitute the value for sigma a prime and sigma m prime, and those equations were written in here. These are the equations for sigma a prime and sigma m prime. Essentially, write the von Mises equation and then substitute the value for von Mises stress sigma and tau a, and then you get this really complicated looking expressions, but they have a structure to it, so it's not hard to see the structure. So let me put substitute 2, which is the equation above, in Roman 1, and we have 1 divided by n equals 8 times, okay, there's a a and there's a b here, which I'll define shortly, pi d cube SC 1 plus 2b SC divided by a times SUT, and this needs to be squared. Okay, we need to take the square root of this. That's about it. So then we can solve for d. We have d equals 8n a divided by pi times SE 1 plus 2p SE divided by a times SUT square half. And then because it's pi d cubed, it will be a third of the whole thing. Okay, so I have defined an a and a b, which are new things. A is just used here.
I think you're missing a parentheses.
My.
You have like One for the
See,
two.
this
then
one
the
ends
square
here.
1/2, and then the 1/3 would be the more like.
Okay, the
split of the-
and
and then there's another one for the
this
entire
one.
thing.
This is the one. Now it's all right. Thanks. Yeah. Did I what? Say that again. Yeah, I have it.
Actually, from last, from like
Yeah,
like
it's right
Monday.
here. Okay, sigma A prime, sigma M prime. Problem. And I've not posted these notes, but I'll post them today. Okay. Good catch on that. There's so many equations. Okay, so I've not defined what A and B is, capital A and B. So here is what A and B is, where A equals 4 times KF A square plus 3 times KFS TA square is 4 KF MM square plus 3 times KFS TM square. Okay. Okay, so let's mock up all those equations which are important. So that's A and B. This is solving for the diameter, and then this is for solving for the factor of safety. Okay, we're almost there. Two more, and then we get to solve. Okay. Next one. Okay, this one is 1 divided by n equals sigma A prime divided by C plus sigma M prime divided by SY. Let's call this 3, and all we do is substitute 1, which was the equation for sigma A prime and sigma M prime, in 3. And that essentially gives us an equation involving factor of safety and D. And so we'll solve for factor of safety first. That's 1 divided by n equals, I need a lot of room for this one. So 1 divided by n equals 16 pi d cubed. Okay. 1 divided by SC, then we have 4 times KF and A square plus 3 times KFS TA square. Okay, so these parentheses have to be, we need to take the square root of that. And then we have plus 1 divided by S y. Same thing, repeat. Something got messed up. I thought it would be too long. Okay, so there'll be a plus, and then this would be sy, and this curly bracket will close here. So it's the continuation. Okay, so we can also solve for D, solving for D.
Wait, so
And
there's no difference in that?
yeah, it's the same. Oh my God, this should be M. There's a minor difference.
MM and TM.
Great, absolutely. So then we can solve for D. Essentially, you can see that in order to solve for D, you just move this to the left side and move n to the other side. And then since it's D cubed, you need to take 1/3. So I have this is the easiest way of doing it. If you're writing this down, you can just try to note that we essentially solve for D by rearranging things. But to be complete, let me just put this here. So I solve for D, and then that would be 16 divided by pi times n, and then this really big bracket here, and it would have 1/3 here. Okay, so that's where it stands. It'll be much cleaner. It'll be without the lines. It looks much cleaner. Yeah. Isn't yeah? That's right. Good catch. Draw. Yeah, I didn't get it here. 16 and what does the dot 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 mean? It just means continued on the next line. No, but if you know this is used in MATLAB. If you want to separate a long line into 2 lines, then you need to do that. Otherwise, MATLAB gives you an error. Okay. Okay, the last one, and then we are done with these length equations. So fourth one is DASME elliptic. Okay, what's that? It's basically 1 divided by n squared equals sigma a prime divided by s e squared plus sigma m prime sy whole squared. And then again, so let's call it 4 first. And then again, the same thing, which is substitute one, which is the equation for sigma a prime, sigma m prime in 4. Okay, and then you have this length equation 1 divided by n equals 16 divided by pi d cube. Okay. Now we have the following things: 4 kf ma divided by se square plus 3 kfs ta divided by se square plus 4 kf divided by sy square plus 3 kfs tm divided by sy square. Okay, since there's an n square, this whole thing in the bracket will be raised to half. Let me check this. If the bracket encompasses the pi 16 over pi d cube or not. It's fine. Okay, so that's the equation for factor of safety. We can also find the diameter. So copy that. Paste. And then what we're doing here is solving for d. So we'll move the d up, move the n down. And since it's d cubed, we need to take this big thing.
Shouldn't the n be on the top?
Oh, n should be on top. 16n. Then we need to put 1/3 here to compress this. Okay, so this is 1. This is the second one. Here, or the Langer line. And then we had these different criteria. So there was the Soderberg line, and then there was curve. Draw it with different colors. So we know that the Langer line, and then so we had this line like this. There's a curve, and was one more which went from here. So then finally we had, okay, so this is the Soderberg. This is the Gerber. This is the ASME elliptic, and this is a good one. Okay, so you can see that there is a region which is precisely here where yield happens before fatigue. Yield happens before fatigue. Okay, and I should maybe put this SY, SE, SUT. So this is the yield line. And this is the Goodman fatigue line. This is the yield line. So you can see for example, the Goodman line, you need to check for yielding because in this region, right here, the yielding is below the Goodman line. That's also true for the ASME elliptic, right? There's a region here where yield happens before fatigue. It's right here between. Okay, so right here, you can see that yield is below the ASME elliptic line. And also, you can see that for the Gerber, it's also true that this line is below the yield line is below the Gerber line. So in all those three cases, you need to check yield before you can be sure that there's no yielding. So in addition to checking those equations which I wrote down, you also need to check yield. However, for the Soderberg line, which is always below this yield line, you do not need to check the yield criterion. So in other words, so let me put down what I said in words, and then we have one more equation we need to remember. So for this diagram, T. Soderberg is always below the yield line, as you can see from the figure I drew, because this is the Soderberg line. So fatigue, so we do not need to check for yielding. However, for D. Goodman and D. Gerber and D. ASME elliptic, there is a region where yield lines is below these fatigue failure lines. Hence, we need to also check failure due to yielding. And what's failure due to yielding? It's the failure we observed in writing chapter 1, where if you take a material and you stretch it, then there's a point where it yields. It changes from elastic to plastic region. And that's basically what you need to do. So what we do here is find the maximum stress, okay, which is now, again, the von Mises stress. So the von Mises stress, we put in sigma A plus sigma M square plus 3 times tau plus tau n. So this is basically the von Mises criterion, right? If you know the principal stresses, sigma and tau, then the von Mises stress is sigma square, square root of sigma square plus 3 tau square. The only change I did here was I substituted sigma as the alternating plot and the study part, sigma n. Now, what we can do here is we can simplify this in terms of MA, MM, TA, TM. And so that is, so just put this as 5, substituting again equation 1, which is what I wrote last class. In 5, we have sigma max equals 16 divided by pi d cube 4 times kf ma plus mm square plus 3 times kfs ta plus tm square, and then I need to take the square root of the whole thing. So once you do that, you can find the factor of safety in yielding, and that's simply the yield strength Sy divided by sigma prime mx. So those are the equations you need to check for failure factor of safety in yielding. And only for those 3 criterions I mentioned. That would be for these 3, D Goodman, D Gerber, D Esmeri. You don't need to check that for D Soderbergh because that takes care of, that rules out yielding if it satisfies the fatigue line. Okay, so let's just put all this what we learned into a problem. In fact, 2 problems.